the islands to the removed islands east receive more precipitation, and the islands to its west receive less precipitation. And I'll explain it why. So for example, when you remove Borneo here, what you will notice is that there is more precipitation over New Guinea. Very, very clear here, very clear signal. And if you look at closely, what we found is that there is actually a less precipitation over Sumatra, and we'll explain why that is the case. Okay. So if we summarize the result in a table, what you are seeing is the following here. Okay. So let's just explain one of the events. So when Borneo and Sulawesi is removed, correct, what you notice is that there is a decline in precipitation over Sumatra by 12%. And there is an increase in precipitation over New Guinea by 27%. So this is actually a huge impact of Borneo over other islands or over surrounding islands. The question is, why did it decrease over Sumatra and why did it increase over New Guinea? And next slide, I'm going to explain that. Okay. So what you are seeing here, let's just discuss the Borneo experiment, correct? If you remove Borneo, how the precipitation will change in different islands. Okay. So for example, here in the Borneo experiment, the precipitation is really explained by those terms, and this is the vertical advection of moisture, basically all the moisture convergence that is happening. So the reduction in precipitation is really due to reduction in vertical advection. So the Sumatra Islands have a least impact on precipitation over islands, and most likely it's because Sumatra is much smaller than Borneo and New Guinea. An increase in precipitation is almost entirely due to vertical advection of moisture, which you can see is that precipitation and vertical advection is more or less same thing here. Precipitation and vertical advection is almost of the same order of magnitude. So the vertical advection is really the dominant force. Same thing here. This is precipitation, this is vertical advection. So no matter how you look at it, a vertical advection of moisture is the dominant reason for reduction or increase in precipitation. However, the decrease in precipitation is sometimes also influenced by the evaporation part, which I'm not going to discuss too much here in detail. Okay. So the question, so why it is happening? So let me try to come up with a very simple schematic that might be able to explain why we are seeing it. So it's a schematic of precipitation during westerlies. So this is what happens. So let's say these are three different islands, okay? This is Sumatra, this is Kalimantan or Borneo, and this is your New Guinea, correct? So when the MJO is propagating, for this particular MJO event, it was not weakened. So I'm considering that it was not weakened, it remained strong throughout. And it led to rainfall over all three islands, okay? So this is very simple to understand, okay? In the next simulation, if you can see, I don't know if you can see it clearly, you can see that there is no island here, meaning that Borneo is now removed. Now, when Borneo is removed, what you are seeing is that there is a lot less precipitation over Borneo or Kalimantan. However, precipitation also reduced over Sumatra, correct? Compared to this, you see that there is a reduction, but precipitation actually increased over New Guinea when Borneo was removed, correct? So the question is, why do we have that? Okay. So what causes this change in precipitation during westerlies? Okay. So to explain this is very, very simple. Why there is an increase in precipitation over New Guinea is because there is absence of friction and obstacles over Borneo, and its topography over land, and its topography increases precipitation to the east, meaning that when the MJO is coming to Borneo, and if there is no land, that MJO can easily propagate and become stronger and lead to much more precipitation over New Guinea. So it's more of a mechanical forcing. You remove the topography, you remove the island, so you should have more precipitation here. So that's very easy to explain. Okay. Now what is not easy to explain is why there is a decrease here, correct? why there should be a decrease in the Sumatra. And the reason why there is a decrease in Sumatra is the following. So there is a decrease in latent heating over the removed island. So there is a decrease in latent heating over Borneo due to decrease in precipitation, which actually decreases the westerly to the west and easterly to the east. And this is coming from a standard wave theory in the tropical meteorology, which is from basically a model called Gill model. So what happens in the tropics is the following. If you have a lot of rain along the equator, correct? So that leads to a particular circulation pattern, which is westerly to the west and easterly to the east. So you can see that there is westerly winds and then there is a easterly winds here. So if you remove this heat source, or if you remove Borneo Island, then those westerlies will actually decrease, correct? And that's exactly what is happening. If you remove Borneo, the westerlies are actually decreasing to the west of the Sumatra. So if the wind is decreased, that means it is actually not able to bring so much moisture that it was bringing earlier. So that leads to actually a less precipitation over Sumatra. Now, there is one very interesting component, because it's a marine science department here, which will be interesting to you, is that our model was atmosphere only model. So it actually did not have any coupling to the ocean. But ocean is actually very important in this case. For example, let's say take this example here. So if you have westerly winds, which are those blue dots, blue arrows, then what happens in the northern hemisphere is you have Ekman transport to the right, and in the southern hemisphere you have Ekman transport to the left. So you actually are bringing warmer water closer to the equator, correct? So the westerly winds are really good for convection. So if you somehow reduce the westerly winds, it will actually rain a lot less over the maritime continent during westerlies or during MJO. So what we believe in our whole example is that whatever decline in precipitation we got in our model was likely underestimated because we did not have influence from ocean. So if you actually use coupling, then most likely scenario will be the precipitation decline will be even more than what we found. So from here, so this is just the summary of the first part, is that the islands overall create a more conducive environment for precipitation. So if all the islands are joined together, then there will be a lot more precipitation. Similarly, because of global warming, if some of the coastal areas are inundated, then the precipitation will actually decline significantly over the maritime continent. And this is very theoretical, the second point, which is established theory for tropical large-scale atmospheric circulation response to heating may need revisit. What I mean by this is the following. What theory tells you is that when the heat source is large, for example, when the heat source is, let's say, 1,000 kilometer by 1,000 kilometer, then it leads to such a pattern in wind response, correct? But what we are seeing in our numerical experiment is that Sumatra is really small, correct? It's not 1,000 kilometer by 1,000 kilometer. It's really small. But removal of Sumatra still led to this circulation pattern. So the theory that suggests that this heat source should be really big may not be correct. Well, at least the numerical simulations are telling that this response can be generated even when the heating source is much smaller, like smaller islands like Sumatra. Okay. So in the second part, I'm going to talk a little bit on the role of topography on the diurnal cycle of precipitation, because you know that most of the rain over the maritime continent happens in the afternoon and evening. So there is a very strong diurnal cycle in precipitation. So again, I'm doing it through numerical experiment, basically the same MJO event that we looked into earlier. And now we have two simulations. one is control and one is flat, meaning that we are removing the topography from the maritime continent to see how diurnal cycle of precipitation evolves. Okay, and the resolution is of course now much higher. It's 4 kilometer because you want to resolve some of the topography over the maritime continent. So this is a really interesting way of looking into the impact of topography. So what you are seeing here is at 00 local time, so it's 12 a.m. local time, then 3 a.m., 6 a.m., 9 a.m., 12, then 12 p.m., 15 p.m., 18 p.m., and 21. So it's 3-hour interval over a particular, over a 30-day period. So these dotted lines, so these dots represent the difference between the simulation without topography and with topography. Okay, and the red line is kind of an average of all the black dots. So if you just concentrate on the red lines, at 12 a.m. what you notice is that there's very little difference between those two simulations, meaning that topography doesn't really have much influence at that time, because these red lines are all close to 0. Okay? Now, as you move further, about 9 a.m., you can see that the red line is now mostly in the negative, meaning that if you remove topography, your precipitation will reduce at that time. And it becomes much stronger around 12 and then 15. Correct? So that's when most of the precipitation happens. So what these numerical experiments are suggesting is that if there are no topography, then the precipitation over the islands in the maritime continent would have reduced significantly. So to summarize this figure, precipitation difference begins to increase where altitude is greater than 1,000 meters. So if you look at those red lines, you can see that at the close to the surface there is not much influence of the topography, meaning that over the flatlands there is very little influence of the topography. So the topographic influence is really confined over the topography only, not on the surrounding that much. And you can see that as you go above 1,000 meters, those differences are becoming much, much larger. Okay. And precipitation difference below 500 meters almost cancels out by both positive and negative differences. So basically there is not much of an influence. So if you summarize the result in one single over the 30-day period, then this is what you see is that within 500 meters there is practically no difference, and then it starts to increase as the topography actually increases. So which is something you'd have expected. Then we ask the question, what processes actually led to this reduction in precipitation? Okay. So I'm summarizing the result. Instead of getting into the actual numbers, I'm summarizing it in a very simple schematic. So what you see here is in the control simulation with topography at 3 different times, 12 p.m., 3 p.m. and 6 p.m. And the reason to choose this 3 period is that's when most of the precipitation happens in this particular model. So with topography experiment, so let's say this is your topography. So you have horizontal advection and vertical advection that leads to precipitation. At 15, that becomes stronger, both horizontal and vertical advection. So you have a lot more rain, and then it slowly reduces. So at 18 or 6 p.m. local time, it is significantly less. Now what happens in the flat experiment is, I think some of the numbers are very small, but in general what is happening in the flat experiment is that so now there is no topography, so that's why those are no longer solid here, and there is a reduction in horizontal and vertical advection that causes a significant decline in precipitation compared to the control simulation. Similarly at 15 and then at 18. Okay. Now, so this is something which was kind of expected, that if you remove the topography, your advection amount will decline, and that will lead to reduced precipitation. But the question that we really wanted to ask is, what is the role of horizontal and vertical advection in the planetary boundary layer and above the planetary boundary layer?